Building fault-tolerant quantum hardware requires mapping millions of tiny physical operations. To organize this, engineers use tensor networks, massive mathematical graphs that describe the state of the system and route quantum error correction codes. This diagram maps the anatomy of one of these networks. The varying line thicknesses between the nodes represent physical bonds, and their thickness indicates their entanglement capacity, the limit of how much quantum information they can carry. But as these networks scale into tens of thousands of edges, they develop blind spots. A group of bonds can lose their capacity entirely, meaning the flow of information across that specific boundary drops to exactly zero. At that point, a chunk of the network is severed from the main system. All logical communication with that sector collapses, and error routing fails silently. This is a topological dead zone. Because these graphs contain vast arrays of multidimensional data, finding one microscopic broken link by hand is agonizingly slow. Hardware engineers spend weeks on manual tracework just to locate a single isolated boundary. This topological isolation creates a human bottleneck. If engineers have to manually hunt down every dead zone, scaling quantum architecture becomes nearly impossible. The standard industry response to massive data sorting problems is to deploy a large language model. AI agents are fast at reviewing dense code and suggesting quick heuristic patches to reconnect these severed networks. But applying an LLM directly to quantum physics creates a conflict of logic. Quantum mechanics relies on absolute mathematical determinism. AI, however, is built on statistical probability, meaning its answers are non-deterministic and prone to error. This split screen highlights the danger. On the left, a strictly ordered physical system. On the right, an AI agent hallucinating. An LLM might try to connect a data path to a node that hasn't been instantiated yet, or suggest upgrading a bond to an infinite value, creating a mathematical anomaly that crashes the simulation software. Deploying any of these unverified guesses directly to a blueprint guarantees catastrophic, silent hardware failures on the physical chip. The TNQG Enterprise Diagnostic Suite was designed to solve this by stripping away the AI's autonomy. It captures the creative speed of the LLM, but traps it inside a rigid mathematical cage. The suite triggers a sweep using the Boykov-Kolmogorov algorithm. It calculates optimal flow across the entire structure, pinpointing the bottleneck where capacity hit zero. This isolated subgraph is extracted and handed to the AI to suggest a localized patch. By isolating the dead zone first, the system leverages the AI's problem-solving speed while preventing it from hallucinating across the rest of the blueprint. The AI's patch is deposited into an isolated physics sandbox. The suite sanitizes the code, clamping unphysical math like negative bonds to valid domains, and sorting operations chronologically. Finally, it reruns the simulation, requiring mathematical proof the capacity increased. Only when a patch yields a verified improvement is it released to the engineers. This loop ensures that the AI's unpredictability never reaches the final hardware design. For engineers, the workflow changes overnight. A search and rescue mission for dead logical qubits that once required weeks of manual labor is now completed in seconds. This chart shows the suite's cost management in action. An unguided AI will often try to fix a dead zone by maximizing the capacity of every bond, creating a massive spike in hardware costs. The suite enforces a resource limit, forcing the AI to solve the problem with the lowest possible physical footprint. It also features a bridging protocol. If the system detects a completely disconnected island of qubits, it forces the AI into a specific bridging mode until those isolated sectors are reintegrated into the bulk geometry. The result is an actionable architectural upgrade that is optimized, verified, and ready for the clean room. Building this system required engineering a backend immune to extreme mathematical loads. By isolating the core algorithms into dedicated processes, the suite can run continuous, heavy simulations without leaking memory or crashing. This architecture provides a framework for integrating large language models into high-stakes engineering. By enforcing a trust but mathematically verify loop, the system captures the creative heuristics of the AI while ensuring the final output never violates a physical law. Caging unpredictable AI within a deterministic sandbox removes the primary manual barrier to automation. The result is a mathematically absolute framework for topological resilience, designed to meet the scaling demands of fault-tolerant quantum hardware.